Hi students, previous classes we have already discussed an AC voltage applied to a capacitor, a resistor and an inductor. We have calculated the instantaneous current passing through the circuits and the instantaneous power of the circuit respectively. In this session we are going to discuss an LCR circuit, a combination of inductance, capacitor, resistor in a series combination. An AC voltage is connected to a circuit consists of inductor, capacitor and resistor, and which is all are connected in series. Inductance, resistor and capacitor. And as usual, we take the voltage passing through the circuit, and their circuit is equal to V is equal to Vm sin omega t. Q be the charge on the capacitor and I is the current at a time t. Then as per the Kirchhoff's rule, we can write L into di divided by dt plus I into R plus Q divided by C is equal to 0. We want to determine the instantaneous current through the circuit and its phase relationship to the applied alternating voltage. And this problem can be solved in two different methods. One, by studying the Phasor diagram of this applied voltages across this inductor, resistor and capacitor. And again another method is to study this relationship between this current and voltage is the analytical method. The Phasor diagram solution of this relationship between the voltage and current. As we see in the figure, this resistor, capacitor and inductor, all they are connected in series with the alternating voltage. Since they are connected in series, the current at any time is same through the all components of this circuit. They are the same, they have the same amplitude and the same phase. So the current can be taken as I is equal to Im into sin omega t plus phi, and that is the current flowing through the circuit, Im into sin omega t plus phi, where phi is the phase difference between the voltage across the source and the current in the circuit. In previous sessions we have already learned the phase diagrams of when an AC voltage is applied to an inductor, a resistor and a capacitor individually, and the phase diagram shows that. And as per the phase diagram, let I be the current, Phasor diagram for the current. And since I and voltage are on the same phase for a resistor, okay, then they are on the same phase. So V are the voltage across the resistor and the current, both they are in the same phase in this case. And the phase difference here, or the phase difference between the voltage and current, that is equal to omega t plus phi here, okay. And then what about this? This is for the resistor, and for the inductor the current lags pi by 2. Okay, and that is the voltage for the phase difference between the current and the voltage across the inductor is, it lags by pi by 2. And for the capacitor, it is ahead of this pi by 2. So this is the phase difference between the current and the voltage across these three separately. Okay, and when we connect them together, and we will get this phase diagram like this. Okay, this is the current across the circuit, and this is then current. The voltage across the resistance is the same phase with current, and for inductor it lags pi by 2, and for capacitor it is ahead pi by 2 angle. The length of the phases of amplitude VR, VL and VC can be written as then VRM is equal to IM into R. The same way we can write for inductance VL M IM into XL, and VCM is equal to IM into XC. So these are the voltage, the length of the phasors for voltage, resistance, inductance and capacitance. This voltage equation can be rewrite by substituting the values of this VRM, VLM and VCM. That can be rewritten as VL plus VC plus VR is equal to V. This equation is represented. See, VL and VC, they are always on the same line but opposite in direction. Now this can be combined into a single phasor, as that is VL plus VC can be combined together. Magnitude of VL plus VC can be written as magnitude of VCM minus VLM. That is the magnitude of this. These two phases are combined together. Since the voltage represents the hypotenuse of the right angle triangle VR, VL plus VC, by this Pythagoras theorem we can write VM square is equal to VRM square plus VCM minus VLM whole square. If we substitute the values of VRM, VCM, VLM in this equation, these are the values, and what we will get? So we can write VM square is equal to VRM is equal to IM into R plus VLM VCM, that is IM into XC minus IM into XL whole square, okay, I square R square. So IM square, here also IM square, IM square. This IM square can be taken out. IM square R square plus XC minus XL, that will remain, okay, and that is equal to, or we can write from this equation IM is equal to, okay, we want to get the relationship between the current and the voltage. VM divided by square root of R square plus XC minus XL square. In each case, as the case of resistance, inductance and capacitance, we have a term which is analog to the resistance. Okay, that is, we call it a resistive capacitance and resistive inductance. So, and on analog to that, and here we can add or we can introduce another term which is called impedance, which is denoted by the letter Z. IM is equal to VM divided by Z. And what is the value of impedance? the value of impedance, and this term is written as Z, which is called impedance of circuit. Thus we have obtained a phase and amplitude diagram for an LCR series circuit with the help of this phase diagram. So this is the graphical representation of this phase diagram. The voltage current relation that we have resolved by this phasor diagram method has certain disadvantages. This diagram says nothing about the initial condition. Anyone can take any arbitrary time t1 and draw the different phases and to show the phase differences between them, and therefore the solution so obtained is called a steady state solution. This is not a general solution, and a generalized solution can be obtained by the analytical method that we are going to see in the next session.